Hi, thank you for stopping by this poster presentation. My name is Omar Carrasco from the University of Texas at Austin. Today, I will be discussing the physical carbon dioxide capture using dimethyl carbonate. As you may know, carbon dioxide removal has been one of the main challenges worldwide in the last decades. Therefore, reducing the atmospheric CO2 concentrations lowers the pace of global warming caused by the increasing human activity, in particular, the one related to energy consumption. CO2 capture and storage, also known as CCS, is regarded as having great potential to reduce the atmospheric CO2 concentration. Among the CCS technologies, solvent-based capture technology is one of the most economically feasible and commonly used. This solvent-based capture technology includes chemical and physical absorption. In the physical absorption of CO2, different types of solvents, such as alkyl carbonates, are used to capture carbon dioxide at high pressures without a chemical reaction. This interaction is important because the driving force is associated with CO2 solubility, which is a different capture mechanism compared to chemical absorption. In this regard, organic carbonate, such as dimethyl carbonate, also known as DMC, is an attractive and interesting solvent for capturing CO2, which has some advantages, including high CO2 solubility and chemical stability. Is environmental friendly because it can be produced from CO2 and methanol and is not toxic. Therefore, in this work, we present the preliminary results of the physical carbon dioxide capture using dimethyl carbonate solution under ambient conditions, considering two main parameters in this evaluation, which are DMC concentration and its chemical stability during the capture process. The experimental section is divided into two components. The first one is related to the CO2 capture experiments, in which pure CO2 gas was bubbled into a capture solution solvent, in this case DMC, under specific conditions as shown in the picture. The second part describes the CO2 capture capacity determination, or in other terms, the amount of CO2 captured. In this evaluation, a sample from a capture solution is taken after the absorption process is complete. Then, this sample is subject to an acid-base titration reaction with hydrochloric acid. The amount of acid is proportional to the amount of CO2 present in the solution. Now, the CO2 capture was carried out using DMC solutions at different concentration. As it can be observed, the amount of captured CO2 increased with DMC concentration up to 12 grams of CO2 per liter at the highest concentration. However, analyzing the CO2 loading capacity, which describes the mole of CO2 captured per mole of DMC used, an optimal concentration of 2% was determined, with the highest CO2 loading around 0.8. Under these conditions, the CO2 capture performance by DMC solution was improved around 7 times compared to the DI water case. Next, the chemical stability of the DMC solution was studied by proton NMR characterization. An analysis before and after the CO2 capture experiment was compared to identify any changes that occur to the chemical structure of DMC. The signal of the proton from the methyl group in the molecule, which is indicated with letter A, remained unaffected by bubbling CO2, which confirms that no chemical reaction took place during the CO2 capture with DMC experiments. Only a physical interaction allows CO2 dissolution in the organic carbonate solution. After completing the CO2 capture experiment, an analysis of the CO2 retention efficiency by the DMC solution was done. As shown in the picture, The CO2 gas captured by the DMC solution stay in the solution for up to 45 days with around 80% of the initial value. This is a considerable improvement compared to the DI water case, where the CO2 retention efficiency was reduced lower than 20% in 15 days. These results demonstrate that DMC solution is a stable capture solvent with an excellent physical CO2 capture capacity. Finally, a comparison between different organic carbonates containing 3 carbon atoms, which is DMC, a linear organic carbonate, and ethylene carbonate, which is a cyclic carbonate, was performed. This test showed that both carbonates are effective in CO2 capture. In particular, the linear organic carbonate exhibited higher performance than cyclic carbonate while increasing the solvent concentration, showing that the chemical structure is key to allow higher CO2 dissolution. Lastly, we look forward to studying the CO2 capture mechanism and kinetics using these organic carbonates, as well as carrying out high-pressure experiments. To conclude, we were able to successfully demonstrate the CO2 capture using dimethyl carbonate aqua solution in a preliminary stage for the development of a suitable physical system to generate alternate carbon carrier solution. Thank you.